Thank you so much, David, and thank you to all the organizers, Camila and Srivatsan, for having me here. So yes, I'm an assistant professor at Yale and also co-founder of Espresso Systems. Espresso builds actually a consensus protocol that is targeting lower latency finality for rollups. So this talk will actually connect quite nicely to other talks that are happening today, including Pod, including Kudzu and Alpenglow and other protocols that you'll hear about in more depth later. But I'm going to focus through the lens of a particular application of consensus to specifically rollups. And what is different or unique about supporting rollups? Well, rollups separate execution and ordering. So originally envisioned as a scaling solution for Ethereum, I actually look at them a little bit differently from a different angle. Rollups have application layer servers that execute transactions and post blocks to an underlying consensus protocol that is relied upon for finality and data availability. I will refer to this as the base layer for rollups. And the key points are that this base layer, the nodes of this base layer, the nodes running consensus on this base layer do not need to execute transactions. So in particular, the nodes individually do not need to receive all the data. They only need to collectively assure that it is available and provide finality over the ordering of the data. Full clients, which I'm going to distinguish from nodes running the consensus as clients that are listening to the consensus, such as an exchange, Coinbase, or an end user running a full node. Full clients derive state by reading data from the base layer and executing transactions. There are also light clients who are not fully executing all the state transitions of the rollup, and they receive validity proofs, such as zero-knowledge proofs of the state. Alternatively, there are fraud games. I won't go into it. It's easier to talk about just receiving a validity proof, since when you have a rollup with light clients that is verifying state transitions through fraud games, the definitions get a little bit more murky. These light clients include blockchains like Ethereum. Ethereum itself maintains ACID bridges to rollups like Arbitrum or Base or zkSync, etc. And a smart contract on Ethereum is a light client for the rollup because it doesn't execute the state transitions of the rollup. And it needs to verify the state of the rollup in order to communicate with the rollup, in order to verify, for example, a withdrawal on the bridge between Ethereum and the rollup. Okay? So I want to highlight in red these terms that I'm going to be using: nodes, clients, because there's so many different words that people use in the consensus world, validators, nodes, etc. So when I say nodes, I'm going to be referring to base layer consensus participants, and when I say clients, I'm talking about people who are not servers that are not participating in the consensus, but are simply trying to get confirmation of what the state of the rollup is. And the rollup could be an application, it could be a general virtual machine, we don't care in this talk. If I mix up these different terms, throw rotten tomatoes at me. I may mix them up because we all mix these terms up, but I'm going to try to stick to nodes and clients. So a quick recap of rollup architecture in more detail. Users send transactions to a server that people call the sequencer. The sequencer broadcasts a transaction list to full execution clients who are listening to the rollup. The sequencer then also periodically posts transactions to the base layer. At this time, the base layer does not execute these at all. It just receives it, makes the data available, and maintains an ordered log of these transactions. Full clients can read from that, verifying the consensus, and check consistency with what they've heard from the sequencer before finalizing their view of the state. This base layer may feature a smart contract called a bridge that also acts as a light client, but we're going to ignore that because that is not an essential piece of this of the base layer. So the main job of the base layer is to provide ordering finality to the sequencer, which is inherited into the state finality of the rollup. So let's say our goal is to try to build base layers for rollups that minimize the finality latency of rollups. What are various things that we can take advantage of in this setting? So the first thing we can take advantage of is that the base layer nodes do not need to execute. They are not voting to agree on the state of rollups that are using the consensus. They only need to guarantee availability and ordering finality of the data. So in particular, not all individual nodes need to receive all the data. They only need to collectively guarantee its availability and finality. So one of the techniques that is possible, which is used in many different systems today, data availability systems, is called verifiable information dispersal, where nodes only receive erasure code shares and not the full data. And I will talk about that more in the next slide. This is going to give an overview of the different topics I'll touch on in the talk. The second thing is removing leaders from the base layer, because rollup sequencers naturally act as leaders already, so they can collect quorum certificates, and then we can remove a hop of an unessential hop of communication in the protocol. And the third thing is more of a question: can we remove a round of voting? So I'll talk about the possibility of just collecting one quorum certificate. For single sequencer rollups, the question is, does a single voting round suffice for finality? There's no leader rotation here because the rollup has a fixed leader effectively, and there's no view changes, and usually 2 rounds are needed to maintain safety and liveness over view changes. There are going to be caveats for doing it like that. And so then I'll also talk about how BFT consensus protocols can achieve a good case latency of 1 voting round when the first round QC contains a higher threshold of votes. And this connects to Kudzu and Alpenglow, which are also going to be talked about later today, although the idea dates back to like 2005 with this protocol Fab, and I'll also present Hydrangea, which is from Kartik, who is a research scientist at Espresso in addition to a professor at Purdue. So, at Duke, sorry. So, for example, if 100% of the votes in so for example, you could, if you get 100% of the votes in the first round, you could tolerate up to 33% false. This is like standard PBFT. If you collect 80% of the votes in the protocol, you could tolerate up to 20% false, and I'll touch on that later. So first, verifiable information dispersal. So this goes back to Avid from Cashin and Tesaro. There are many papers on different flavors of verifiable information dispersal. The idea here is that the leader computes an erasure coding of a block and of vector commitment to that erasure coding, and distributes shares, so components of this erasure code vector, to the different voting nodes. Okay, each voting node receives 1 share. The share size is the size of the block divided by P, where P is related to the erasure code itself. So if we want the property that if we have an ideal code like Reed-Solomon, then if any P fraction of the shares can recover the block B, then the share size will be of the size of the block divided by P. Now, we're distributing it over all the nodes, so we also divide by n. So the total communication, if you multiply by n, is going to be B divided by P. So it's going to be a constant amount of communication in the block as opposed to sending B, the size of B times n. So you're saving more and more communication the more voting nodes that you have. So this can help both for throughput, but also for reducing latency, because you have to communicate less data overall. Now there's 2 options for verifiability. The first option is for each voting node who's receiving the share to verify a proof that C commits to a correct code word, where the ith component is indeed this share that it is receiving. But if this is done on the critical path of consensus, then even though we're reducing the amount of data that we need to broadcast, we're computing this extra proof. And so if this happens on the critical path of consensus, it can actually kill the latency gains that we achieved in the first place. So there's this beautiful idea that was, I believe, first introduced in dispersed ledger, which is...
I'm going to trade mics with you because you talk with your hands a lot. So.
Okay. I talk with my hands a lot. I should put mics on my hands, actually. So the voting nodes only verify that they received the correct component C. So they'll verify, for example, a Merkle path. And then we push it to the state derivation function of the rollup itself in this case. Oh. Only problem with this is... Okay. So yes, so we would push it to the derivation function to skip improperly dispersed blocks. So for example, if C is determined later, and this could be done through a proof, to not be a correct commitment to a correct code word, then the state transition function would just skip over it. So we push it off the critical path of consensus. So this is a very good thing to do if you want this technique to save latency. So the second thing I mentioned is rollup sequencers are effectively leaders, especially if we're talking about rollups that have centralized sequencers. And so having the rollup sequencer send the block to a leader of the base layer consensus wastes a round of communication. So because each sequencer is still semi-permanent independent leader, now there are caveats to this, right? Because there's also forced include transactions that you want to get through on the base layer. You may have sequencer failovers where if a sequencer goes down for a period of time, then you use the base layer consensus to introduce a new sequencer. You may have rollups that are sharing sequencers. I'm not going to get into the nuances of this, but each sequencer is already a semi-permanent independent leader, therefore we should take advantage of that. And one way to do that is essentially to implement multiple parallel instances of consensus. So if you have each sequencer basically acting as a leader, then the base layer doesn't run one consensus, but effectively runs a different consensus protocol for each a rollup in parallel. You can imagine if it was only one round of voting, it would just be a very simple protocol that actually looks exactly like pod, right? Where you just have nodes listening directly to sequencers as clients, voting, and then handing the quorum certificate back to the leader, okay? And if we have multiple rounds of consensus, you would just go through multiple rounds with each sequencer. So connecting to that point, does that suffice actually? Does it suffice to have one round of voting only, especially in the setting where we have a fixed sequencer? So normally consensus requires at least 2 rounds of voting to maintain safety and liveness over view changes. But for rollups with a fixed sequencer, let's just say this sequencer collects a single QC. So let's say that it's 2/3 of the votes are required for a QC, just like in PBFT, Tendermint, hot stuff, etc. And let's say that that's all we do, just sequencer distributes to the nodes provide votes, and as long as the sequencer can collect 2/3 votes, then it can convince clients that the block is final. So we also need to make sure that nodes only vote for a block extending a prior block with a valid QC, and will never vote for conflicting blocks for the same rollup at the same height. Okay, so what might go wrong if clients treat this single QC as confirmation that a block is final? Well, at first glance, it seems okay, right? Because quorum intersection, maybe this is an application of pod, right? So quorum intersection prevents equivocation, as Dionysus was talking about, right? The sequencer can't collect QCs for conflicting blocks, but the sequencer can split the voting nodes by sending conflicting blocks to each to say half of the nodes. It can cause a deadlock. But the fixed sequencer is already responsible for liveness, so maybe we don't care about that. There's a caveat though, right? Rollups don't really want to have the property that a single sequencer could permanently kill the rollup liveness. Right? They would need to have some kind of unlock mechanism. So let's give a straw man. Let's say let's say there's this independent BFT consensus protocol, maybe it's the base layer, maybe it's something else. And in the event that a sequencer deadlocking all these voting nodes, then we'll try to get out of it by using this, by leveraging this separate BFT consensus protocol. Okay, so we can have nodes basically send some timeout message through the protocol with their latest lock, very similar to how recovery mechanisms work in regular consensus protocols. And once enough timeout messages are seen, let's say the nodes just leverage this BFT consensus protocol to elect a new sequencer and block extending the highest QC. So the reason why this doesn't work, okay, it seems to work at first glance, is that any unlock mechanism must involve listening to clients. Remember, clients are distinguished from nodes that are participating in the consensus protocol. A client could be like Coinbase, which is not participating in the consensus protocol. And if the sequencer collected a single QC and gave it to Coinbase to convince it of the finality of certain transactions, and then didn't distribute that QC to any of the other nodes participating in consensus. So for example, maybe it broadcasted B to 2F honest nodes. It corrupted one node, collected a QC of 2F plus 1 votes, gave it to the Coinbase. But none of these nodes here ever saw that QC. Then they may end up going through some recovery mechanism that completely ignores the fact that Coinbase saw this QC. And so we'd have to have Coinbase participate. We'd have to do something like have a solicitation period where all clients that got convinced of finality of transactions would actually present the QC to the voting nodes. We could have a solicitation period like that. It's a big change to the model. Like, I don't know that Coinbase would feel comfortable doing this, but basically anyone who relied on the finality would have to now pay attention to timeouts and participate in unlock mechanisms to protect themselves. So it's a big change from the way clients participate today. So the question is, okay, can we have consensus with a good case 1 QC path that doesn't require clients who are relying on this 1 QC confirmation to stay online and participate in the consensus protocol? Okay, and so the answer is yes. There exist protocols where the number of nodes is 3F plus 2P plus 1. They tolerate up to F Byzantine faults in the worst case, but when P at most F nodes are corrupt, then clients may confirm upon seeing a single QC of size n minus P. And there are many works starting with FAB by Martin and Alvisi in 2005, and Kudzu and Alpenglow, which you'll hear about today, match this result as well with a simplex style protocol. So FAB was kind of more in the PBFT-style realm. And so let's look at some examples of this. So for example, if you have P equals 0, then you can tolerate 33% corruption, just like Tenderman or Hot Stuff or PBFT. And in the good case, if you get 100% of the nodes voting in the first round, then you can actually just confirm. Another setting would be P equals F, so you could tolerate 20% corruption, but you need 80% of the votes in the first round to get a QC. And this is the setting that Alpenglow and Minimeat use. You can get another example where P equals F over 2, 25% corruption, and the good case QC would be 87.5% of the votes. So hydrangea is another paper in this line of works that just came out recently by Nivesh, Aniket, and Kartik. So Kartik's a research scientist at Espresso, which is why I'm focusing on this in particular. But the nice thing about it is that it generalizes these results in a way, although it provides a particular protocol in the PBFT hot stuff style. And it looks, in addition, at crash faults. So it says for n equals 3F plus 2C plus K plus 1, the protocol can tolerate F Byzantine faults and also C crash faults. And nodes can confirm upon seeing one round of n minus p votes as long as p is less than or equal to c plus k over 2. And nodes will confirm in one round when at most p nodes are faulty. Because if at most p nodes are faulty, then we will actually get n minus p votes in the first round of voting. So example parameterizations here would be, let's say that c equals f, k equals 0. So this could tolerate 20%. It could match all the results that we said on the other slide. But in addition, let's say that we have 20% crash faults and 20% Byzantine faults. the good case one round QC would be 90% of the votes in this case. Another parameterization would tolerate only 13% Byzantine, up to 20% crash faults, but the good case QC would only require 80% of the votes. So let's give just quick intuition about how this works. So what can go wrong with a single round of votes? So suppose a client confirms block B upon seeing 2n/3 of the votes. Suppose no consensus node saw 2n/3 of the votes, and thus none locked on B, even those who voted for B. So in this case, nodes locking on B without seeing a QC, this can lead to a deadlock. If a leader change occurs, then the next leader proposes and could drive consensus around a value B prime that's not equal to B. Okay, so this is what goes wrong with just a single round of votes. Right? So the first observation is that nobody locked on B, okay, but 2n/3 nodes voted for it. So why not provide this info to the next leader and have them use it? Repropose B. So a problem that can arise here is that if the first leader is malicious and gets 2n/3 votes for B, and then n/3 votes for B prime, then it could use that to get a client to confirm B. The next leader would wait to hear from the first 2n/3 nodes. It can't wait for more because up to n/3 might be faulty. So it may receive n/3 votes, honest votes first for B prime, and then n/3 Byzantine votes, and it will think that it can't distinguish the fact that 2n/3 votes were collected in the first round for B, and it will propose B prime. So just listening naively to see what people voted for in the first round doesn't work for this reason. But a second observation is that the problematic example requires Byzantine parties to equivocate during the leader switch. So this leads to the question, well, what if fewer faults are Byzantine and the rest are only crash? Or what if we require a higher fraction of votes to get the client to confirm with one voting round? So let's look at the setting of hydrangeas. So let's set n is equal to 3f plus 2c plus k plus 1, and p is equal to c plus k over 2. There are at most f Byzantine faults and c crash faults. Suppose some client confirms B upon seeing a QC that consists of n minus p votes. Let's call this set of nodes providing these votes Q1. Let's look at what happens during a leader change. So during a leader change, nodes send their current locks and what they voted for to the new leader. In this case, the new leader receives at least n minus f minus c of these locks, because at most f are Byzantine, at most c are crashed. Let's call this set Q2. Let's look at the intersection. So the intersection is size at least 2f plus p plus 1. In pictures, we have Q1 over here, parties that voted for B in view V. We have Q2 over here, the set of parties who sent view messages to the new leader. They intersect in 2f plus p plus 1, at most f of which are faulty. So that means we have at least f plus 1 honest parties who are basically telling the new leader that they voted for B in the last view. So we've shown the leader receives at least f plus p plus 1 votes for B. The new leader cannot receive this many prior round votes for any different value B prime. If it did, then we can argue a contradiction. Right? If it did, then the set intersects with the n minus p nodes who voted for B in at least f plus 1 nodes, and there's at least one honest one who then equivocated. That's a contradiction. So we know it sees at least f plus p plus 1 votes, and it can't see that many votes for anything else. So the new honest leader is A, safe to propose B once it sees f plus p plus 1 votes, and 2, it's guaranteed to see this and propose B in the case that n minus p nodes voted for B in the prior round. Now, this sketch made several simplifications that are handled in more detail in the paper. So we only considered consensus on a single value rather than a sequence of values. We only considered a single view change. We didn't consider what to do if nodes had locks in the prior round, preventing them from accepting a new leader proposing B. We didn't discuss how big the quorums need to be on the slower worst case path. There are many other details, but that hopefully provides some tuition and also provides some intuition for the results that we'll see later in the day, although in a different setting of the simplex protocol. So thank you very much, and I hope you learned something from the talk.
Any question for Ben?
Yeah.
So this is all great, and I also spent some time myself on this like long time ago. But what happens in real systems is that delta is not delta. It depends on the position of the server on the network, like how, like on speed of light and how far are you from there. So when you translate all what you're doing to practical systems, like what are the implications, right? Because like searching for optimal latency on paper and on whiteboard is one thing, and then when you translate it to actual systems is a completely different one.
Yeah, well, this is also why in the real world setting, it's good to have protocols that have optimistic responsiveness, right? So any PBFT-style protocol has optimistic responsiveness. You don't need to know what delta is, right? This is in the partial synchrony setting, and so when we say good round latency, we mean that if you collect 80% of the votes in a QC, then you can confirm a client right away. So we don't really need to worry about knowing what the delay in the network is. If we're dealing with synchronous protocols, then that does become a problem. Yeah.
Thanks, Bill. So yeah, kind of just a general question on the broad range of consensus protocols you have, with the parameterizations. Do you notice sort of any like minor? Do you notice the difference is becoming more minor and minor? The more sort of trade-off you start making. Do you think there's sort of like a broader pattern going on, which is sort of ideal or something that should be strived for?
Actually, somebody in the audience who's, I think, thinking about this a lot is Victor. So, there's like these simplex-style protocols, these PBFT-style protocols, right? Both of them can now achieve the result that I was saying in this protocol, like which is a better protocol. I don't really know the answer to that. At Espresso, we've been building on the hot stuff style family of protocols. We do find that in the end of the day, there are also a lot of implementation details that just go into minimizing latency that don't have to do with the number of rounds in consensus, right? We think that the rounds in consensus are the only thing affecting latency, but there's so many other systems level factors, right? So I don't know if that's the best answer to your question, but hopefully it addresses it. Yeah. Great.
Okay, cool. Thanks a lot, Ben.
Yeah.